Hey everyone, welcome to 8.4. We're going to go through solving one more type of radical equation, and then we're going to move on to more variation functions with non-integer exponents, so more model problems. We'll get started with one today with the notes. So first, let's look at our last type of radical equation that we're going to solve. So same rules apply. We need to isolate a radical, raise both sides to that index, and then go from there and see where it takes us. But our ending might look a little different this time. So as we begin, we should see we've got one radical already isolated. So we're going to go ahead and square both sides. When we square that left side, again, if you need to make that side note to square that binomial, please do so. I'm just going to jump straight to what we should get. So 2 root 2x squared, we should get 4 times 2x. 2 root 2x plus or times 1, but we're going to double that, so we get plus 4 root 2x and then plus 1. The right side, we just get 4x plus 9. The radicals go away. So I notice we still have a radical. Let's clean things up. So we have 8x plus 4 root 2x plus 1 equals that 4x plus 9. All right, let's bring everything over except for the radical to that right-hand side. So we have 4 root 2x equals negative 4x plus 8. Now what I do notice is that those three terms all have a 4 in common. So if I can divide everything by 4, that's going to make squaring things a lot nicer. So I go ahead and I do that. So dividing everything by 4, we're left with the square root of 2x on the left. Negative 4 divided by 4, we have negative x. 8 divided by 4 plus 2. So now we can go ahead and square everything again. And when we do, the left side, we're just left with 2x. The right side, squaring that binomial, we should get x squared minus 4x plus 4. So now we can set it all equal to 0. So we get 0 is equal to x squared minus 6x plus 4. Okay, this looks similar. However, with a quadratic, we always try to factor it. Two numbers whose product is 4 but adds to negative 6. It's not going to happen. So what do we do this time? Well, now what we have to do is we have to use the quadratic formula. All right? So our quadratic formula. Let's go ahead and set that up and see where that takes us. So as we solve, we're going to get x is equal to opposite of b, so 6 plus or minus the square root of our b term squared, so negative 6 squared minus 4 times our a times our c all over our 2 times our a. So as we clean this up, we're going to get 6 plus or minus. That's going to become 36 minus 16. So we should just be left with 20 underneath that radical all over 2. As we continue to simplify, 6 plus or minus the square root of 20 simplifies as 2 root 5 all over 2. Noticing each one of these terms, we can divide by 2. And we end up with x equaling 3 plus or minus root 5. All right, so checking our work isn't going to be so nice, right? Because we have radicals within radicals. So what we can do to check our work is we can use our calculator, okay? So we can use the calculator to check. So what's that going to look like? Well, I'm going to plug x equals 3 plus root 5 into my calculator. And when I do, I get approximately 5.236, and it keeps going. Store this value, okay? And now you can use that stored value to check your work in the original equation, okay? So now you're going to go through 2 times the square root of 2x plus 1, whatever that x value was, that 5.236. And when you plug that into your calculator, all right, you're going to get the left-hand side to be 7.47, around there, all right? When you plug in the right-hand side, the square root of 4x plus 9 with that stored x value, you're going to get about 5.47. So obviously those don't work. So x cannot equal 3 plus root 5. So now when we check x equals 3 minus root 5, we would throw that onto the calculator, and when you do, 3 minus root 5 is about 0.763, etc. Store that value. Okay, when you check that on your original equation, you'll get the left side to be about 3.47. When you throw that x value on the right side, the square root of 4x plus 9, you get about 3.47. So this guy works. So our ultimate answer here is x equals 3 minus root 5. All right? Okay, so you needed your calculator there. Now we're going to get set up with this model problem. You'll need your calculator handy for this as well, but we're going to get into variation functions with non-integer exponents. All right, so a little different than what yesterday's classwork dealt with. All right, so this actually comes from page 440. It's number 9, the microwave oven problem. I like to refer to it as the bacon problem. So the number of minutes it takes to cook bacon in a microwave oven depends on how many slices you put in at once. So that's a very key, important piece. The number of minutes it takes to cook depends on the number of slices. Okay, so minutes depends on slices. So that's going to help us define some variables here, right? So we can say S is the number of slices, and T we can say is the number of minutes cooked, right? Okay, so a popular brand often specifies that 1.75 minutes for 2 slices and 2.5 minutes for 4 slices. So that's going to help us kind of create some ordered pairs. But this first part A says, explain why the number of minutes does not vary directly with the number of slices. Well, let's take a look. I'm going to plug these into a table, right? So we have S and we have T, and I'm going to kind of zoom in. When there's 4 slices, it cooks for 2.5. Let's do it reversed. Let's talk about 2 slices. We cook for 1.75 minutes. For 4 slices, we cook for 2.5. So what are we looking at? If we're talking about variation, remember it's that multiply, multiply. So what do we do here? Well, we times 2. Okay, 2 to 4, we're multiplying. So in order for it to vary directly, 1.75 times 2 would also have to work. But that's not the case, right? So how can we describe this? Well, we can certainly just say that doubling the slices does not double the time. Okay? So we would need a times 2 on both sides in order for that to be a direct variation. But now let's move on to see if we can come up with what the actual equation is. So we are going to assume that the number of minutes varies directly with some power of the number of slices. Okay, not necessarily an integer power. So we're going to use the 2 given ordered pairs to derive the particular equation, expressing the number of minutes in terms of the number of slices. All right, and we'll go through that together. All right, the system of equations you get after substituting the ordered pairs can be solved, but we have to be a little bit creative. So let's see where this takes us. Okay, so we are given the fact that T varies directly with some power of the number of slices. Okay, so it's going to be something like this. All right, now if we use our two ordered pairs, now I'm going to do this in a particular order for a reason. So our first ordered pair, let's use the 4, 2.5. And I'm going to plug that into our equation. All right, so we're going to get 2.5 equals k times 4 to the a power. And then we'll take our other 1.75, and we'll plug that into our equation. So 1.75 equals k times 2 to the a power. All right, now this is a system of equations. We have two unknowns. We have to solve for k, and we also have to solve for this power a. All right? So instead of doing some addition and elimination that way, what we can do is we can divide these equations. All right? And when we divide these equations, the k's cancel. So what are we really left with? We are left with 2.5 divided by 1.75 equals 4 to the a over 2 to the a. Now remember our rules with these exponentials. We can rewrite this, right? We can combine these. So this is like saying 2.5 over 1.75. I'm not going to figure out what that is yet. Okay, equals 4 over 2 to the a power. Oops, sorry. To the a power. And 4 over 2 is just 2. So we really have 2.5 over 1.75 equals 2 to the a power. Okay, how do we solve this? We're not getting common bases here, so we have to take the log of both sides. So I'm going to zoom in over here. So taking the log of the left, so log of 2.5 over 1.75, moving the a out front equals a log of 2. And so now we get a is equal to log of 2.5 over 1.75, all divided by log of 2. And we should get our a value to be approximately 0.51457, and it keeps going. So guess what we need to do? Store that value. Okay, so store that value, and now we're going to use that to help solve for k. All right, I'm running out of room here, so try to bear with me. I'm going to zoom in, and we'll solve for k. Okay, so when we solve for k, oops. I'm going to use one of those ordered pairs. So I can use the 1.75 equals k times 2, and now our stored value of a, 0.514, etc. Okay? And now to get k, we just divide by that 2 to the 0.514. So 1.75 over 2 to the 0.514, etc. Use that stored value, and we get k to be 1.225. So k works out nicely. All right? So now we have our k value and we have our a value, the power. We can go ahead and write our equation. So our equation is going to be the following. T equals 1.225 times s to the 0.514, etc. So there is our final answer. What you need to do and what you'll need to do in class tomorrow is finish problem 9 from page 440. So there's C, D, E, and F left to do. If you have questions, let us know.